Consider the mass spectrometer shown schematically in the figure below. The magnitude of the electric field between the plates of the velocity selector is 2.8 times 10 to the third volts per meter, and the magnetic field in both the velocity selector and the deflection chamber has a magnitude of 0.03 teslas. Calculate the radius of the path for a singly charged ion having a mass of 1.9 times 10 to the negative 26 kilograms. Alright, so this is a diagram the problem gives us. We got the magnitude of the electric field in between here, 2.8 times 10 to the third volts per meter. Magnetic field is 0.03 teslas. The mass of the particle is 1.9 times 10 to the negative 26 kilograms. In the charge, it said just singularly charged, which is just the elemental constant 1.6 times 10 to the negative 19 coulombs. It's asking us to find the radius out here of the path of the particle. And obviously down here, the electric field points to the right because you got positive charges here, negative charges here. And all these little X's in the background mean that the magnetic field is pointing into the picture. So, to find the radius, we just got to use forces. Out here, we have FB is equal to MA. We're assuming that there's no gravity here, so it's like in space. We know FB for a particle is Q times the velocity times the magnetic field. And since it's moving in a circle, because magnetic field can only affect the direction of the motion of a particle, instead of acceleration, we're using v squared over r. The v on this side cancels out with the v squared. Okay, now we just gotta solve for the radius. Multiply both sides by the radius, divide both sides by q times the magnetic field. R is equal to mv over qb. And that's great. We have that. We have the mass, have the charge, have the magnetic field, but we don't have the velocity. What do we do for that? Well, the answer is to look in this part here. So the diagram shows us that the particle is moving in a straight path. And if it's moving in a straight path, that means all the forces must be balanced. So let's draw a quick free body force diagram. We know that since it's a positive charge and the electric field points to the right, we have the electric force pointing to the right. And then we have a positive charge moving upward and an inward magnetic field. Using the right hand rule, current is the first finger is the current going up, middle finger is the field going in, and our thumb is the magnetic force. We can see that the magnetic force is to the left. And they have to be equal in magnitude since it's not accelerating in either direction. And from this we can write FB minus FE is equal to 0. Bring FE to the other side and substitute in our values. We know QVB is equal to Q big E, which is the electric field. Q's cancel out. We get a velocity that is equal to the electric field over the magnetic field. And this is true for every scenario in which a particle is being pushed through a magnetic field and electric field while maintaining a straight path. So we plug in our values from that. The electric field is 2.8 times 10 to the third volts per meter, which is 2,800 volts per meter. Over the magnetic field is 0.0300 teslas, which results in a velocity of 93,333 meters per second. That's not our answer. We've got to bring that in, put it in up here. It's from before, R is equal to mv over qb. We know that R is equal to the mass, 1.9 times 10 to negative 26 kilograms, times the velocity we just got, 93,333. Charge, 1.6 times 10 to the negative 19 coulombs. And magnetic field, 0.0300 T. This results in a radius of 0.3694 meters. This problem was originally challenging to me because, like I said before, I was not able to find the velocity. I did the part out here right and solved up to here, r is equal to mv over qb, but I didn't know what to do from there. Since the problem didn't give us a velocity, I didn't know what to do. And I realized we'd use this part here because just by telling us when in a straight path, we know that the forces both must be equal, meaning the magnetic force must be equal to the electric force, meaning the velocity must be equal to the strength of the electric field over the strength of the magnetic field. And this problem shows my growth as a physics student because it shows that I'm able to apply both magnetic and electric forces acting on the same particle. This setup here is actually a voltage selector or a mass spectrometer. It's what scientists use to determine what kind of particles are in something. So this basically just shows that I understand the physics and the science behind one of those devices. Thanks.